Okay, so I will start with a result of Waltz projet that we'll try to reprove. So we have the theta correspondence which depends, so you fix some psi in additive character on trivial and we have a bijection between cuspidal representations of PGL2 and 2 such that pi L half pi is non-zero, and it doesn't matter here if it's a partial L function or not, and genuine psi-generic cuspidal representations of the double cover of SL2, save for some exceptional guys, so orthogonal to kind of classical theta series or Weil representation. And this is achieved, this is not just some abstract bijection, it's achieved actually by explicit construction using the Weil representation. So I will not recall exactly this construction, but I will do it in another way following Ginzburg, Rallis, and Sudry. So this is, of course, so it goes back to Shimura, the classical setting, and then Shintani in the other direction, and Waltz projet.
Put mass first.
Okay.
Especially about the other direction he did it.
Ah, okay, good. So we are talking about things in the 70s and early 80s.
50s.
Okay, mass, of course. Prehistory. So now let me formulate the result of Waltz projet. It's a reformulation. So yeah.
I'm confused. Does L half pi? This is a bijection with the. It needs this L central L value condition.
Yes. Did I make it wrong?
Oh, sorry.
Did I make any mistake?
No. Oh, I see.
It's zero, otherwise it's zero.
I see, but you can change the character psi to get the other.
Right. Oh, yeah. So it's very important. So depending on psi. Depending on psi.
Yes. Okay.
That's of course very important. Yeah, and maybe actually this is in my note. So yeah, before that, let me just remark. So changing psi. So psi to psi a, meaning which is psi of a times the variable, changes in as much as it makes sense, because of course the L function condition can be destroyed, but it wants to change pi to pi tensor, the Hilbert symbol like this, the quadratic character corresponding to the Hilbert symbol with a. So with respect to the f square root of a mod f. Yeah. So this bijection depends on psi. Suppose I start here on the right hand side with the same representation. So it goes to two different things. Let's say it has psi and psi a Fourier coefficients. Well, it won't go to the same thing if I change the psi. It will go to the twist of pi. And this is important. Okay, anyway, so now let me formulate the theorem. Is that, so suppose, so pi tilde corresponds to pi under this theta psi correspondence. And okay, let's assume that f is totally real this is for analytic reasons, not for arithmetic reasons. And pi infinity is discrete series. So if you like a Hilbert modular form or something. But again, this is not, it shouldn't be there, this restriction. Then, for any phi in the space of pi tilde, that's on the SL2 tilde. And this is on PGL2. Okay, let's write it here. Because it's the central L value, so that will be in the center. So the Fourier coefficient square, and this is an equality, it's not up to constant, it's actual equality. So you have some factors. I will write and then explain. Okay, so what's going on here? So this is the Whittaker coefficient. Of phi tilde. I should put phi tilde. Consistency. Of course, I split the unipotent in the cover. So it's volume 1 to be sure. And the Peterson inner product again, volume 1 normalized. Okay, so these forms are on SL2 tilde, but the product is on SL2. Okay, so this is just the partial L functions. This is the symmetric square of pi, so and the standard L function of pi, but only the partial one. And this is kind of the Fourier coefficient of the matrix coefficient. So let me just make a few remarks about this. So Weizmann didn't formulate it exactly this way. At that time he still formulated things with actual modular forms and actual. So it's kind of a classical setup. And of course, he didn't leave any constant to imagination, so to speak. Oh, sorry, these are the S integers.
S is sufficiently large?
Yes, yes, of course. So, of course, S contains infinity, 2, all the things above this, and phi is Ks invariant. Yeah, this is a standing assumption. I will stop making it. That's, of course, always.
So you discussed this last time. In the Piaget case, it's clear what the stable integral means.
Yeah, yeah.
In the real case,
right, so yeah, I will say that. Yeah, okay, so just first remark is that Weizmann gave a more explicit formula for this in a classical setting. The advantage here, I think, that it's a little, at least, easier on the eyes. But of course, if you really want to compute something from this, then okay, you're not exempt from doing the local computation. But at least it gives you some framework. Okay, and then some other. So these Fourier coefficients. So look, notice that this is the same psi that I use for the theta correspondence, but this has something to do with the SL2 tilde. So if you want to compute another Fourier coefficient, okay, you go to theta lit with respect to that character. So that will entail this twist of pi. It doesn't change the denominator, but it will change the numerator. But you can get every coefficient. I mean, psi is arbitrary, just so the theta lift is determined by psi. But these the Fourier coefficients on the left are related also two toric integrals, I don't know how to call it, so periods over tori on the PGL2 side. So if it's the same character, it's a split torus. If it's another character, then it's a non-split torus. So you can, so there are various related statements here which are kind of morally equivalent. So there's a whole slew of results of this nature. And then, but of course, unlike, at least I should say that unlike in the, so he phrased it, of course, meaning, you know, so the Shimura correspondence, right, it's between half integral weight modular forms. And integral weight modular forms. And but the difference between the integral case and the half integral case is that in the half integral case, namely PGL2, so the Fourier coefficients are not simply the Hecke eigenvalues. I mean, once you normalize the first one, then everything else in GL2 is just read by the Hecke eigenvalues, as we all know, but that's totally not true in the half integral case. You can only read a square class this way, but the point is that the other ones are given by this much more fancy way of L functions. So it's harder. I mean, all this kind of Lindelöf stuff is much harder. I mean, Ramanujan relates to Lindelöf. Okay, I mean, I'm not going to make any story about this, but just mentioning it. And okay, so to answer, yeah. So the stable integral on the right. So again, in the periodic case.
Ramanujan becomes Lindelöf in the great plane.
Can be, I guess.
That's true.
So the stable integral on the right for the periodic case, this I explained last time. It's the integral. It's the limit of the integral over the let's say FV compact open of the same thing in the discrete topology. So it's kind of the best way you can make sense of it, and so this is a directed set, and then the Archimedean case just converges, and that's the assumption on pi infinity, by the way. So we don't have to worry about the meaning of that. Yeah, and the independence of S this is just amounts to a Kassaman-Shalaika formula in the interplectic setup. Okay, so for SL2 tilde you can kind of do it by hand, but it's actually true more generally. This was proved. But somehow any way you prove it, you also prove this in some sense. You don't use it necessarily. Okay, any questions or comments so far? Just about the formulation. Okay, so as I said, Walsh-Paget used the theta correspondence to prove it, but I want to present another proof, and which generalizes in a different way. So the theta correspondence, of course, generalizes also to high rank, but I want to describe something else. So I'll present some alternative proof, to say alternative facts. So this is the joint work with Mao, where I will then explain how to generalize it, and which is based on the descent method, which I will explain, of Ginzburg, Wallis, and Sudry. Okay, so the first order of business is just to tell you something about Eisenstein series. So I will just do things at the case at hand for simplicity. So consider, so G will be SP2. For me, it's 4x4 matrices. And I will consider the parabolic subgroup, which is the Ziegel so-called parabolic. So M is GL2. So in matrices, it's something like that. This is GL2 here, and this is M and M star, the evolution. And so I start with, so pi is a Caspian representation.
Just to be clear, your SP2 is what? If
4 by
everyone
4.
else is SP4.
Right. Of GL2. So at this point, I don't assume yet a central character condition. And let A pi be the space of all smooth functions on GA, which are left invariant under the rational points of M and the adelic points of U. So U is, by the way, symmetric 2x2 matrices.
Wait, so can you just give us an overview of what's going to happen before?
Well, I have to set some notation. Sorry. So yeah. So smooth, such that all the translates belong to the space of pi. I just have to normalize. This is the modulus function, which in this case, by the way, will be determinant to the 3/2 after I do the -12. Okay. Okay, so that's for all G. So this is like an induced space. I mean, it's isomorphic. It's just a realization of the induced space as automorphic functions, not on GA mod GF, but GA mod UA and F. So standard thing. And for any phi in that space, I construct, as usual, the Eisenstein series. Phi S, so S is a complex parameter, G is the group variable, phi is a section. It's a sum of phi S gamma G. Somehow the only way to make something automorphic, to average. So what is phi S? For phi S, it's just a way to make all these induced spaces with a twisting on the same space. So in the Iwasawa decomposition, this is determinant to the M to the S, otherwise it's the same. So M is in GL2, K is in the standard maximal compact, and U is in U. That's in terms of the Iwasawa decomposition. And so this series converges, so let me just list a few facts. So the first fact, or the 0th fact, is that the series converges for real S sufficiently large. In this case, it would be like 3/2. So now, of course, this is Langland's theory on Eisenstein series. So it admits neuromorphic continuation. This is easy fact. The hard fact is that it admits neuromorphic continuation. In the functional equation, which reads as follows. So it relates S to minus S, but it has this gadget, the intertwining operator. So ms goes from to a of the contragradient of pi, defined in the same way. So is the intertwining operator defined by the usual integral, which I'll write down in a second, and it converges exactly when the Eisenstein series converges. I mean, the convergence is essentially the same. So ms of phi at the point G will be the integral of phi s w u g. So W is this Weyl element. Again, so it doesn't matter so much, but the volume is normalized to be 1. And so again, it converges for real S large and admits momorphic continuation. And it satisfies after analytic continuation, M minus S composed with MS is the identity. And
The U is the top.
sorry?
The U.
Yep. Thank you. And MS star is MS bar. I mean, this is a simple adjointness formula. So means that MS is unitary for real S equals 0. Of course, after you homomorphically continue it, and so in particular holomorphic. And so the intertwining operator comes in several ways here. So, okay, it comes in the functional equation. It also comes in the computation of the constant term.
Erez, but the way when we do the intertwining operator, when you look at the local intertwining operators, you don't get that identity, do you?
Right, no, locally not. This is a global.
Not.
This is global, sure. Locally I get the Planck-Arens measure. Okay, so the constant term of the Eisenstein series is given by, okay, so EU, which, okay, so this is, by definition, this is the integral, okay, UF, and it's given by the original guy, which of course is not surprising because this is one of the summands, and then the intertwining operator. Okay, technically it is something like that, and that's of course a fundamental computation, especially combined with the Gindkin-Karpelevich formula, or the Langlands extension of it in the p-adic case, which tells you that the intertwining operator is given mostly as a scalar, which is the L function. In this case, it's a standard L function, or the partial, times that of the central character of pi. And the denominator is more or less the same, except with a shift. So this is kind of the main thing, the global part, times, yeah,
Non-sensitive to X.
times the local intertwining operator. So that's Jay's question, local intertwining operator. Okay, which is defined in a similar way. And this thing, I mean, let me just point out that this thing is, in a more conceptual way, this is the L at 0 of pi times the determinant of R, where R is the adjoint representation of. So you have the L group of G, and then you have inside it the corresponding parabolic, and this is the adjoint representation of ML on the Lie algebra. That's the general formulation. But of course, this is one of the most remarkable computations, I would say, of the 20th century, because that led Langlands to the invention of L group, and the rest is history. Anyways, Peter, I know that Peter is giving a course on Eisenstein series, so I don't need to tell you more things.
I will end with analytically continue. That's all I'm doing.
And okay, so the next point is that the poles of the Eisenstein series are governed, are in fact the same as those of MS, and therefore basically by this L function, at least for real S positive. I mean, we don't. We are too scared of the denominator, of course, being 0, but that will not be our concern. Sorry?
Constant controls for all
Sure. Right, but if you just want to say that the numerator control thing, then you better shy away from the zeros. Well, I mean, we don't want to get into that kind of mathematics. So, so that's for all S. And so in particular, ES is holomorphic on the unitary axis, and it has finitely many poles for real S positive, and they are all simple and real. And finally, I guess the fifth point. So if you have such a pole, then the residue, which I would denote sometimes by star if S naught is clear from the context, this is just a definition. Irritaglable automorphic form. And its inner product, let's say with itself, is given by the inner product of the, so this is on MA, or if you like on GA mod MF UA, okay, times part of the center. And this is meaningful. This is on G. And well, of course, M star is the residue of the intertwining operator. So the Eisenstein series somehow plays a double role. It plays a role in the continuous spectrum, of course, but it also plays a role in the discrete spectrum, and that's very mysterious sometimes. Anyways, so this formula, again, this is very important because, I mean, that's, for instance, the starting point of Langlands' kind of youth paper on the volume of the fundamental domain. Basically boils down to the computation of this. And also, so Peter wanted me to mention, so I will do that. So in the case at hand, so the only possible pole, so this is not going to have poles, but this may. That happens if omega pi is trivial. So so such a pole exists, well, in fact, if and only if omega pi is trivial, so then you get the dead equation. And that will be at S naught equals 1/2, of course. So that means that pi lives on PGL2. But and L half pi is not 0, right? Because this L half pi may kill the pole if it's 0, and it can vanish. Okay, so this formula gives, I just mentioned it, that it gives us the L half pi is in fact, well, in this case, when it's not 0, it's positive. I'll just write it like this. I mean, again, if omega pi is equal to 1, because the point that all other terms are essentially non-negative, so you just get a priori non-negative, so you just get the non-negativity of this just because the left-hand side is non-negative.
I think my homework I gave you was to explain it in general.
Sorry?
I ordered this last week, but in the general form of all L functions which are non-negative, I guess you can say a word how you could do it.
Yeah, okay, when we get to the GLN, I will. But I wanted to start with this case because maybe it's a little easier to explain things. But I mean, most of the ingredients are already in this case. I will explain what's how it works in general later.
Actually, I think the first person to ever use this construction as a residue effectively was Subota. Exactly with half metaplectic threefold cover. This is how we got the equidistribution of Weil sums for cubic characters. I mean, he has his book on Eisenstein series, and then he wrote this beautiful little book where he computes the metaplectic Eisenstein series. The geoterm, the imaginary quadratic field things picks up the pole. And that form is the channel of the theta function. I mean, that was a precursor of Patterson. There's nothing about it. No, but the idea.
I mean, the setup, of course, works also for covers. Yeah.
General, the idea that you can actually, as long as you can, in the constant term, you can recognize the pole, you can do something interesting.
Okay, so now if we considered, so we can consider the non-degenerate Whittaker or Fourier coefficient of this Eisenstein series. And of course, we will get to the Lagrange-Shahidi theory, so to speak. So, okay, so this is formally this thing. Okay, so n is the full, is the maximal unipotent, so upper unit triangular, and psi n is the non-degenerate character. Of NA trivial on NF, so that means that it picks up the simple roots, both simple roots. So in this case, this is another fundamental computation, that this is equal to the so the psi n is a non-degenerate. So explicitly, if I have here x, y, and then minus x here, psi n could be psi of x plus y, for that matter.
When you compute it not the constant term, but a
non-degenerate Fourier coefficient. I already computed the only non-zero constant term. Now I compute the non-degenerate Fourier coefficient with respect to the full maximal unipotent standard. Say, and then this is Shahidi's computation, which reads, so now I have integral over UA and then pi U phi S psi n U du. So well, so first of all, this omega, this W, whatever, is just the Fourier coefficient of the original section, so inside the GL2, so to speak. And then, so this is just unfolding, all the other orbits cancel, and then the computation is that this is what you get from this. When you do the unrivaled computation, you get exactly the denominator of the intertwining operator, no numerator. Of course, you still have the local integral, which you have to deal with, and which is the same thing. I should say, actually, here, Shahidi, of course, he writes it in his paper, but the real computation here is Kassim and Shalaika. The formula for the Whittaker function, it all comes down to that. And that's, of course, a very important calculation, because it leads to many, it leads to understanding better the L function and the use of it for the converse theorem, etc., etc. I will not get into that, but on.
By the way, Kubota is also the first to observe, as far as I know, the use of that to prove non-vanishing L function on line 1.
For GL2 or for covers?
Just for GL2 and things like that. But what I'm saying is he made this observation that you got a non-zero coefficient in order to prove the prime number theorem using the Eisenstein series. Of course, Selberg, when asked, said he knew it before the whole precise. It's in Kubota's book.
Okay. So so I won't get into any of that issue. I just want to mention it, just for some perspective. But for us, so the kind of the flip side of this, taking the non-degenerate Fourier coefficient, is that it kills the pole. So because there is no numerator, the residue will not have a non-degenerate Fourier coefficient. So that means that you lose something. You gain something, you lose something, as always in life. But so you can look at other things. So the Eisenstein series has more information. As important as this computation is, it still hides a little bit. So it has more information in its bowels, so to speak. Namely, you can look at the coefficient, the following coefficient. So now I take the long root, the non-simple long root. So let's look at that. This is not. This will not going to lead to a non-degenerate coefficient. At least not for the standard parabolic. Anyways, so I'm going to view it as an automorphic form on the stabilizer. What's the stabilizer of this? It's the G prime semi-direct product with V. So where G prime is SL2, sorry, and V. So this is a maximal. It's a unipotent radical of a maximal parabolic whose levy is so L would be the GL1 times SL2, but I will not take the. Because of the psi, I don't take the GL1 part.
But a non-zero Fourier coefficient along another parabolic.
So it's not the full. So you see, this is not abelian.
No, but it's a uniform.
Well, so this is a Heisenberg group,
Yeah.
and I'm not taking the integral over V. I just take the integral over this, the center, right? I just integrate the center. The center of V. So this is the center of V, and V is the unipotent radical. So I have Q is equal to L times V.
So it's just a Jacobi.
Right, so that will of course lead us to this Jacobi coefficients, exactly. And so now the point is that, so okay, the board suffers everything, right? But the point is that this will not, so if I want to further expand it, so okay, so locally, so this is a Heisenberg group, and I took this omega pi, and this central character. Right. No, automorphic form, just automorphic function. Yes, automorphic function. I'm not claiming anything more, but of course we'll soon claim some more things. And if I want to expand it, then, I mean, so locally, of course, as you know, there is a unique representation with this central character on the Heisenberg group. So the sensible thing to do is to look at the, okay, so first thing first. So locally, there is a unique representation, the Stone von Neumann representation, on the Heisenberg group with this central character. And on this representation acts, because it's unique, acts the SL2, but not by representation, but rather by a projective representation. So that leads to the Weyl representation. So the sensible thing to do is to take this Weyl representation into account. So in other words, we will consider this object. So for a Jacobi, I guess in this case just usual Jacobi coefficient. So I will integrate on V against a theta function. And now I will face the metaphyletic cover. Okay, so well, as usual, this theta function. Okay, so it's theta function on this group, if you like. It's given by sum over the lattice over F of some Weyl representation applied to phi at xi. So what's the notation here? So phi is a Schwarz function. So the Weyl representation will be denoted by omega psi. This is the Weyl representation of this group G prime or G tilde on it acts on the Schwarz functions. And it acts by the usual formula. Let me just recall for you. So for instance, omega psi of so this part will act by translation. The y part by multiplying by character. Okay, of course, the central character will, the center will act by its character. There's a half here, doesn't matter.
So is it true that somehow the residue at one of our poles is the theta function?
The residue of the Eisenstein series?
Your Eisenstein series, when it has a pole.
Yeah, but the residue lives on G, so what does it mean?
But restricting to this.
Okay, we will come to that, of course. We'll come to that. I'm sorry if I'm too slow. I just want to get the notation straight. So everything is up to root of unity, and of course it's inevitable because I have to go to the covering, but anyways it doesn't matter so much. So this acts by a multiplicative translation, and finally not finally, but so the unipotent inside acts by multiplying by character, but not of xi, rather of alpha. So there's a quadratic thing here, and finally these elements acts up to a scalar is the Fourier transform. Okay, so that's the Weil representation in its simplest case. Okay, so now we come, after we set the pieces on the table, so to speak, we can start to play chess. So the Shimura type integral.
Sorry,
Yeah.
what is G prime?
Oh,
G prime?
sorry. G prime is SL2 in the middle. Yeah. So this is SL2 here. So the Levy part is.
Sorry. So you were describing the representation of SL2 semi-direct Heisenberg.
Right.
Okay.
Yeah, that's how we think about the representation. It's really a representation of that. So it's a Stone phenomenon representation on the V part, and the SL2 acts on it, or rather the cover. And that's the formula up to, as usual, I mess things up with the characters, but that should be essence of it. Okay, and now we come to the Shimura type integrals in this context. And again, so the theory here is also due to Ginsburg, Wallis, and Sudry in this, of course, higher generality. So what you look at finally, so that's to answer people's questions. So you look at this Fourier Jacobi of this Eisenstein series, not yet the residue. I just take the Eisenstein series itself. And what this turns out to be, it turns out to be a kernel of some L function. So in more explicit terms, if I integrate it, if I take Peterson inner product against, so now this of course is a function, this is now a function on G tilde, right? Automorphic function on G tilde. I was forced to pass to G tilde because of this representation business, I mean how it acts the G prime on the Stone phenomenon representation. So if I take this, so phi prime is a class form on G tilde prime, then you can do unfolding here, and what you get is the integral of G prime A mod N prime A of, okay, I'll start here and continue in the other board. Okay, so first things first. So this group is N prime. This is the maximal unipotent of G prime. Yeah, I will explain now the notation. So the W prime. Sorry? Yes, thank you. Yeah. Of course, this construction you can do for any automorphic form, but we do it for Eisenstein sets. Not that it's uninteresting for other groups, for other forms, but that's what we do. And this is just the Fourier transform, Fourier coefficient. And this I will explain in a second what it is. So of course it has to be some Whittaker function with respect to maybe to the inverse that you start from the thing on G and you get something on the G prime. So it is some transform which gives you some Whittaker function on the G prime. G prime is SL2. People keep asking this, so I should have highlighted. The G prime is the GL2 part in the SL2 part in the Levy. Sorry?
SL2 or SL2 tilde?
So when I write G prime, I mean SL2 when I write the tilde. But of course, when I take Peterson inner product, it doesn't really matter because the product lives on the G prime. So I hope this will be clear from the context. But yes, I mean this gadget lives on phi prime and this lives on G prime. The product lives on G. Okay, so I have to explain what is this, but before that, let me just tell you. So this is unfolding, but now the question is what are the local factors? And the local factors are the. So you get the numerator will be as usual a partial L function, but now it depends on psi. Let me write it and then explain. Okay, so if I want to be precise, I also have this. So as usual, I always get the denominator. This is always, I mean, you know, kind of a priori that you would get it. I mean, otherwise it cannot work. And then you have a local integral, which of course will involve these global objects. One of them is written here, and the other I'm yet to define. So this is this A phi. Okay, so what is this A phi business? So this is some transform which will give me some Whittaker function on the G prime. So it's given by this formula. The formula is not terribly important. I just want to write it to set the record straight. So W, I think the W phi G. Yeah, let me just, because I didn't. So W phi G is this one. It's the same thing. Let me now. Yeah, because I didn't finish. So the V.
Could you read what you wrote in that integral?
This one?
Yes.
Okay, so it's the integral of V A mod V prime. So V prime, I better tell you what it is. So V prime is actually this group. And so it's V mod V prime, and then this W function, which is there on that board, just the Whittaker function on the GL2.
Yes.
And then phi, and then this is an element, this is some Weil element, which actually was before, so this was this
Yes.
I2 minus I2, and the W prime is actually this one. This is W prime. So it's a Weil group inside the G prime. And then the rest, I hope, is legible. So this is phi at 1.
So before we had L of S, I mean, so in the most predicted formulation we had pi instead of pi times pi conjugated. Is that right? I'm trying to compare this to
No, I mean, we changed the setup, so let's not. I mean, so of course, maybe that was. So this is now in the space pi tilde. So at this point, I don't assume anything about pi and pi tilde, except that, okay, of course, pi is cuspidal and pi tilde is cuspidal. So now pi is what you started with on GL2, and pi tilde is on G prime tilde, on SL2 tilde. But I don't assume any connection between them. So the point, so this function, the claim is that this automorphic function on SL2 tilde is a kernel for this L function. What is this L function? It's the tensor product L function of GL2 times SL2 tilde. Now, to make formally sense of it, I have to choose psi because it's Stucky isomorphism depends on psi. But you can make sense of it, and that's the result. Any questions about the formulation, at least?
this was, I thought this was supposed to be another proof of the same.
We're not yet. We're not yet there. We're not yet there. We are still making preparation.
I mean, so can you say, I mean, are you going to say why? I mean, when you work with Jacobi groups, in some sense, you're all, I mean, it's morally equivalent to working with half integer weight, right?
Well, okay. So maybe just wait with your question just a few minutes. Bear with me, and maybe this will be explained.
Can you say what kind of function of this psi is? So you start with a.
Yeah. So.
We start with phi, which was in the induced
Mhm.
representation from
Mhm.
the parabolic.
Mm-hmm.
But actually, you start from the Whittaker model of. You're inducing a Whittaker model.
Yeah, this is just the way to realize it. Yes.
And then you're pairing with the vein representation.
Yeah. So. Okay. So.
Slave representation.
Okay. So morally, I would say that this is kind of a nothing burger. I mean, it won't contribute any L function or anything. You can first approximation ignore this integral. Locally, it will just be one almost everyone.
What would be one?
this extra integration. I mean, of course, this is the Whittaker function, but this extra integration is basically nothing almost everywhere. I mean, for particular G prime, so you can ignore it as first approximation. But it's just a transform to get you some Whittaker function downstairs.
And the evaluation of phi at 1 is precisely that point which gives you something of Whittaker type, right? When you evaluate the capital phi, you evaluate it as 1. That's precisely the point.
What is capital phi? Oh, yeah.
Right.
Yeah.
That's precisely the point where G prime acts like the unipotent.
Yeah, I mean, of course, that will give you the character, yes. That will give you the character because of this formula, xi is equal to 1, yes.
So altogether, so this is Whittaker on G prime, but it is also something on the, you have semi-direct product of G prime with V.
Mm-hmm.
What is the equivariance property of this with respect to?
Well, I just integrated, right?
So what is the answer?
So the answer is that it's equivalent after, so it's kind of home. It's tensor with omega psi. It's an element. How do you call it? It's like it's factored through the equivalent, but with the omega psi. Whatever. So it's some. I mean, locally it's some kind of JK module, but you twist by omega psi. So the character, it's a representation.
Okay, that's the source. From to where?
So this A, okay, this A technically, okay, I will probably when I write it I will make a mistake, but it's something like home. To some Whittaker space, space of Whittaker functions. Something like that.
Which is probably invariant under the diagonal action of G prime.
Well, home G prime, yes.
But you have G prime acting on both, though.
Okay, I mean, I just want to say that, I mean, I force it to be equivalent the right way. I mean, it's the only sensible way. Okay, so now let's pause for a second. I mean, we shouldn't, so we'll make a real pause, but just a didactical pause for now. So if you taking residue, what does it tell us? Well, if we take residue at s equals half, we know that this is the only potential pole. What we will get, so I told you that this is nothing to, there's no pole from this, but there is a pole, of course, from the L function. And so if you want to get a pole, that means that you'll get a pole for the L function. Now, when does the L function has a pole? So when does it have a pole? Well, that's when this L function has a pole. It's at s equals 1, and that exactly means that pi tilde lifts to pi. Well, if you like Shimura, lift or factorially. So in other words, what this suggests is that, almost proves, is that the residue of this, and that's Peter's question, the residue at s equals half of this Fourier Jacobi guy is exactly, so if you start with pi with a trivial central character, otherwise there's no chance for a pole, this will be the, okay, I guess in this direction it's the mass, you said, the mass lift of pi. Or the Shintani, or whatever you want to call it. So from GL2 to PGL2 to SL tilde. Right, because this will kind of this will be the thing that you pair with to get, sorry, here, to get a pole. That's exactly what the L function will have a pole. So now we can just forget about history and just define it this way, and that's what Ginzburg-Morris already did, of course, in a more general setup.
A question. If L of 1/2 pi was 0 in this,
Right.
You could still, that the residue of the Eisenstein series, there would be, I guess, some cap representation instead of it. Right?
Oh, you're right. You could do many. You're right that you could
So to speak,
play
the same.
many.
And would you have the same relation with? Would you expect that for your Jacob?
Yeah.
Residue replaced by that guy?
Yeah. Yeah. So many things just work kind of at the level of unrived computation. They are not sensitive to how
But
you.
think, but globally, that you would expect the same.
So what does it mean the same? I mean, it would be something which would be compatible locally.
Yeah.
But you could certainly do it, and people do it. And
The way
Yeah.
you're normalizing things, what is the L to normal the residue? The residue of the Eisenstein series.
so that's given by this M star, right? So and that's the residue of the. I mean, so on the unitary axis, the L,
Which
the
L factor? Because I don't.
that was the
So
L.
would that cancel some L factors if I? Okay.
What is it? Sorry. You see, the Eisenstein series is kind of, it wants to be L2 on the unitary axis, except that it's not L2. But,
We're
other-
not the unitary axis.
but we are not, right? But this is.
So if I take my section 3 to be
Let me just take 3.
so that the residue
So that
is
will be
not 1.
residue of zeta. This will be 2. Sorry? Yeah.
On the top of the right board, if I take my section so that the residue has not 1, do some L factors cancel?
Well, sure. I mean, the denominator
Well, you look
is
at
common.
adjoints at once.
But okay, I mean,
For example, I don't want to see L pi in the denominator, for example.
Yeah, that's true.
So this is a discrete homomorphic representation of the residual alone. So I'm asking what is the formula I could normalize by itself to norm instead of.
yeah, I mean, I think that these factors will sort of cancel. That's true. But yeah, okay, except that it's kind of a square root. So, but we will pair it with another formula. I mean, maybe things will become more clear. But I don't know. Maybe it's a good point to take a break now. Okay, so what we did, let's just recall. So we first claimed that for any pi capital on GL2, you take this Fourier Jacobi of Eisenstein series, that will produce you this kernel function for the L function of the tensor product L function. Namely, if you integrate it against any Cas form on the SL2 tilde, you will get this L factor in the numerator. Of course, you have some denominator from the Eisenstein series and local integral. Note that, by the way, this vanishes unless phi prime is generic. I didn't have to assume that phi prime is generic, just that it's Caspidal. This computation would still be true, except that it's 0, it gives you 0. So that somehow, it knows how to pick up only the generic guys. And then the other remark that Simon asked me, and that's an important point, that so when I take a residue, so it means that this L function has a pole, but that actually implies that the original Eisenstein series has a pole. I mean, I can certainly take a residue inside the Fourier Jacobi. The Fourier Jacobi is a compact integration. It doesn't produce, I mean, I can put the residue inside. So that means that if this has a pole, then omega pi is 1 and L half pi is not 0, because that's the condition that the residue.
So
of the Eisenstein series.
There is some exterior square that is hidden here.
Right, of course, in the general case, there is exterior square instead of the central character. So that.
And even in this calculation of the local.
Yeah, no, of course. I mean, the intertwining operator, everything has.
Yeah.
Instead of central character, it's exterior square, absolutely. I hope we will have time to cover this as well. But the essence is really in this case. So we define. So again, given pi cuspidal on GL2 or PGL2 with L half pi not 0, we define the descent to be just the space of, or the span, if you like, of this Fourier Jacobi of this Eisenstein series by taking residue. So it's really like a tensor product of spaces, and that's a space. And the theorem of Ginzburg, Rice, and Sudbury is that this is an irreducible psi-generic representation of SL2 tilde, which weakly lifts to pi in the sense that almost everywhere the parameters match, but that's technically there's a psi always in this business, and that of course, in fact, this is nothing else but is just the Shimura or the inverse Shimura, whatever you want to call it, Shimura lift or theta lift. Okay, so it's just another construction, if you like, but it's applicable in other case, in high rank situations. And now to finish the story with the Walsh-Berger theorem, well, we need also.
Components is also higher rank, so.
Right, but it's an. Yeah, so you can generalize the Shimura correspondence in several ways. So one is, of course, with the SO2n plus 1, but this is with the GLN. That's the difference. I will explain.
GLN is on the pi.
Right, so the pi here, it's kind of secretly on SO3, but I think of it as GLN, it will generalize to GLN, or GL2n, actually. The SPN tilde will remain the same. Okay, but to complete the story, I need to tell you not just what is this, but also what is the Fourier coefficient. So how to prove, so why is this non-zero? I mean, we can write anything that we want, but why is it non-zero at the end? Well, that comes up, so there are several ways to think about this, but one way which gives you some information is compute and show that it's generic, so compute a psi Fourier coefficient of this gadget. So what happens if we compute this W, what they call W prime of this Fourier Jacobi guy? So there is a very nice formula for that, which actually involves the same gadget that showed up in this Ginzburg-Sudbury integral, namely this A thing. So this is going to be, so it's another fact, that this is nothing else but, let me just write it carefully. Yeah, so this is the A of M star of W. You can put a G prime if you want. So this is literally the same operator applied not to phi but to the m star of phi, the residue of the intertwining operator. Now, unlike this formula, which makes sense for all s, this is only, so to speak, after I take residue. So this is not in kind of special, some, as far as I know, more general identity. So it's more specific. So this, I will also circle this fact. Okay, so now we are pretty much in business, because we can compare the two formulas. So we can specialize the formula that I wrote down. Namely, we can take a residue for the inner product and compare it to the Whittaker, and then we get something in the spirit of Wells-Perger's theorem. So I had it here, maybe I should raise it. So it's visible. Okay, so let us compare. So take phi prime to be this typical element in the descent, namely Fourier Jacobi of the Eisenstein series residue. Okay, and compare the inner product with the Whittaker, or with the Whittaker square. And remember, the quotient wants to be this L factor. So morally, if we just ignore the local factors, we just look at the partial L function. Yeah, so I mean, so hidden here that actually this A phi here, maybe I could take it over Fs in this picture. Okay, because as I said, the local factors don't contribute almost everywhere. So what did we have? So the phi prime, the inner product, what was it? We just need to take a residue there. And of course, remember that pi tilde is the lift of pi. So what we will get in the numerator is ls pi with itself, or its dual, so it doesn't matter, over, okay, we have this zeta f2, and then L3 halves pi. So I have zeta f2 from two sources. One is just taking s equals 1 here, and the other just for my measure. Shouldn't confuse them. Times, okay, times this Whittaker of phi and the Whittaker of phi prime. So just the hand waving. Sorry?
What's that number that in the denominator?
Oops, sorry. 3 halves pi. Yeah, sorry. Yeah, so I mean, this just don't take it too seriously. This is just kind of moral picture. I will make it more precise. I just want to see that it matches before we start to do anything local. So just everything is in quotation mark here. And then the Whittaker phi prime, just by this formula.
Sorry, what did this moral statement come?
No, this is just taking residue in this formula here. This is taking residue. So taking pi to be the lift of pi tilde and taking residue at s equals half in this formula. Okay. Here. The inner product, because I took phi prime to be the Fourier Jacobi of the, it's exactly the residue of the.
That's for
Yeah. So except what this, okay, so this is just roughly what's going on. And then the W phi prime, but what I said here in the computation of the,
So where did the W phi come from?
well, it's here, right? I have the W prime and I have the W here in the A.
Oh, in
Yes. Okay, while the W phi prime is given by this formula, so this is the residue S equals half of zeta f at 2s. I mean, of course, I input the formula for the intertwining operator and then take residue over L3 half pi zeta f2 WF. I mean, there should be the L half pi. Guess I forgot. So that's 1/2 of the residue at 1. Okay, L half pi. L3 half pi. Just F2. Fine. So what I want to say is that the quotient what you will get, so one of the factor cancels, and then you just end up with a residue of the Rankin-Selberg over, and then there's 1/2 here. Okay, and then the residue of zeta f 1 and L3 half zeta pi. So yeah, so this cancels, this thing and this thing cancels. Remember, one of these cancels, then the rest cancels here, and then the rest, that's what we get. And that's essentially the Weizmann formula, right? So if we ignore the local stuff, this is okay, we're in business. So what about the local stuff? We don't want to, I mean, there's a limit to the amount of cheating that we're allowed to do. So what this computation shows, this computation reduces the formula to a local identity. So let me spell out the local identity that one needs in order to justify this argument. So we need to get to a local picture. So from now on, now F is a local field, and pi, let's say a generic representation of GL2. But soon it will be on PGL2. So, and I can look at the Whittaker model of pi, and I can look at the induced picture to in SP2, and I can do the same construction. So this is realized as a space of functions from G mod n G mod n. So on n I will have a character psi n, which is not so trivial on u and non-trivial on the m part.
Erez, in the story, could you have taken phi to be an Eisenstein series itself?
Yeah, of course, and that will come up later. But I mean, in this case, nothing will happen because it's a GL2, and I need it to. But if it's GLN, then I have space to fit in. The unrifled computation doesn't change. It doesn't. I never use that phase capital in the unfolding.
Yeah, I was just wondering if that can help with the local computations, because Eisenstein case you know that.
Well, locally, I could still have a super-Caspian guy. Okay. Yes, so what do we need? So now I can define the same way the A phi. So in this realization of the induced, I will just take, okay, the same formula. So V mod V gamma. Now everything is local. So I will get some, so this will be some Whittaker function on the G prime, on the SL2 tilde. And it will give me some space of functions. So in principle, I can look at this space Now, when I apply, so locally, it's not the residue, it's just the value at 1/2. So I have intertwining operators from this induced space shifted by S to minus S. And of course, at 1/2, something special happens because I get a Lagrange quotient, a genuine Lagrange quotient. So I can look at this space, and I can just define it to be the local descent. Now, of course, phi is a Schwarz function on F. And that's, of course, compatible with the global descent.
This is a set of what?
This is a space of Whittaker functions on G prime. If I'm lucky, this will be an irreducible representation. But it's realized already in its Whittaker model, or Whittaker space. So the claim is indeed that if omega pi is 1, then this space, again, a space of Whittaker functions is irreducible. So, namely, it's a Whittaker model of some representation pi prime. And by the way, so as I said, this integral doesn't pose any problem. Periodically, it's compactly supported. In that Archimedean case, it's Schwarz function. But the M1/2 actually turns out to be always holomorphic in the generic case, if omega pi is equal to 1.
Whether A sub phi factors to the Lagrange quotient, right?
Well, by definition, it factors to the Lagrange quotient.
Yes, because you have the intertwining operator.
Right, I applied the intertwining operator. I mean, let's say that we are tempered or something close to that. But the thing, but it still doesn't mean that it's irreducible, right? I mean, the M1/2, the image is irreducible, but the A phi thing, it's unclear that it's irreducible. Now it's on G prime. So this is a representation of G prime, or G prime tilde. So there is a statement here, but it's true. And then, so the local identity that, this putative local identity here reads, so for all W in this induced space, okay, and W check, okay, I guess in the dual space, and okay, phi and phi prime, phi and phi check Schwarz function. So if W prime is this descent, this A phi M1/2 W, well, technically I have -1/2, so yes. Okay, this is just notation. Then what I need to match the, so now unfortunately I erased it, but to match the formula for the inner product with the formula for the Whittaker, and to get the theorem of Weizmann is, so I have to have, remember there was this stable integral over n prime. N prime was the unipotent of SL2, and then I have this inner product which was given explicitly this way. And then the A. And I take for a coefficient of this inner product. And that should be just the Whittaker function at E. Actually, it's at -E. You have to make sense what is -1 in the metaplectic case, but that's not a big deal. Let's ignore this. And then this A phi psi inverse of M1/2 W. The identity, I'm sorry that it becomes a little invisible. But so again, how did it come from? Well, so I just want to take the, remember we had something like pi tilde of this n, phi, or now it will be like phi prime. That was the right-hand side in the Weizmann formula. So this is now this becomes the left-hand side, and that should match the Whittaker. After I kind of ignore all the L factors, which that was this is what I showed here, then it all boils down to this kind of identity. So there are no really, I mean, it's really an identity kind of on the nose. Of course, you have to be careful with the measures a little, but it's just an identity, no some, obscure. Okay, yeah, sorry. So the left-hand side is some strange Fourier coefficient of inner product, and the right-hand side, I will rewrite it. So it's a W prime at -1 times the A pi inverse, if we check, at the identity of M half W check. Well, technically shifted by -1/2. Remember that's supposed to be what I get. This is kind of the descent of W at the identity.
To clarify, you have reduced obtaining the precise Volkswagen formula from this analysis to this proving this local identity.
Correct.
So what was its last 1/2?
Oh no, well, okay. I mean, you can ignore it. It just the technical meaning of MS is that, I mean, when I trivialize the section of the induced by S, then I always do this shift by S. So I have to shift it back just for consistency, but this is not so important. Yeah, so that's what it boils down to. It's beginning is hard to digest maybe, but so again, this local identity implies plus global formulas that we wrote. These two global formulas imply and almost equivalent up to, I could have some factors which multiply to 1, of course, but otherwise, one second. So about the convergence, so okay, this was the stable thing that I mentioned before. This, yeah, this actually you have to, so in the template case, this will converge. And even if you're unitary, that's still okay. So for the safe side, pi, let's say that unitary. Sorry?
You mean the thing you start from?
Yeah, the pi. Yeah, the pi. Now we are in a local situation, and for convergence issues, so let's just pretend that it's tempered, but it still works, even if you're a little bit off the temper for convergence. I mean, locally things converge better than globally. Anyways, convergence is not an issue here. I mean, only for this part, which can only make sense as a stable integral. And so let me just explain what comes into this proof of this local identity. So what comes into the proof, I will say it briefly. So what we have here, I mean, let's just separate the pieces. It looks a little threatening, let's say.
What's the nature of this?
Yeah. So
the slides give you functionals on the same transformation.
Right. So yeah, I should say that a priori this is true up to a constant. This I know that it's true because this is, yeah, and I should say it right away, the Weizmann formula. I mean, the two sides, because of uniqueness of Whittaker, I know that the two sides are, they have the right invariance. So the
uniqueness
of Whittaker for SL2 tilde.
Erez,
Yeah.
maybe it would help to say what is the analog for GL2, because you mentioned it last time. So if you replace the inner integral by the pairing between Whittaker models, you get the same statement for GL2, right?
Yes. Okay. So for GL2, well, well, okay. So it's this kind of inner product but okay, then I still have to do the yeah.
outside
Okay.
integral and will give you the
Yeah.
values at the
Okay. Good. So if I had something like that, I think Akshay asked me last time, is it legible? Maybe not. So if I formally do this, so W of T1 shifted by 1x01 and WT1, let's say, with a bar. So this is an inner product. Without this, this would be an inner product, and then I take the matrix coefficient of this element and take Fourier coefficient. And the claim is that this is just W of the identity square. And the reason is that what happens here is basically Fourier inversion, right? Because when I pull out the x, I have psi of Tx. So this is like taking the Fourier transform at x of the function, you know, on this variable, which doesn't make sense at 0, but still I can pretend, and then taking the Fourier transform again at 1. So that's what. So this is basically Fourier inversion.
But why is that analogous to what?
Right. So the thing is that, okay, so clearly the outer integral has a similar nature, and the inner integral, I want to say that this is some kind of inner product. And that somehow should be perhaps be clear from the global integral that I wrote before, which is it still around? Yeah, at least one side. I mean, so this reflects, this is the local counterpart of this global integral. I'm afraid I already erased the local counter. But you should take my word that, sorry, you can take my word that this is the local counterpart of, when we unfolded it, that was, oh, it's still written here. Okay, so that's exactly what we have here. So this is kind of a genuine inner product. And I want to say when I integrate this inner product against psi, I want to get back just the Whittaker function, the identity square. So that was a good suggestion of Yanis. So this is really analogous.
But sorry, both sides are functional from which space with which invariance?
on the Whittaker space of this residual of the irreducible representation of G prime.
G prime is S12.
Yes.
But these guys are some induced larger.
Right, so a priori, so the W check, I mean, of course, so the W prime is in the descent space. The W check is only on the big space. And so there's no M half here. It's only a posteriori, only on the right-hand side. It's not clear that this a priori factor through the M half.
But if you're going to get the constant by some method, you probably get, you can evaluate it with the G something and see everything from, well, maybe explain how you done it.
Okay, so how do we prove this? So there are, so first of all, let's just parse this expression. So I can first I can play a game with an S. So I can look at formally at this expression. Sorry. Now W and W check are anything. I don't take the MS. I just look at this. Okay. And so before just the inner integral, just the inner product, but not even taking just this expression.
I think you kind of highlighted the identity is only when S is a half, right?
Yeah, the identity only has equals up, but parts of it are true. So I'll try to explain. So I claim that this is, again, this is, so now let's just ignore what, let's assume that all integral converges, which is not the case, but just for the sake of argument. So what I will get, let me write and then explain. So this is kind of Ichino-Ikeda formulation. I claim that kind of on a formal level just because, I mean, of course I use the fact that I induce from the same representation pi. But otherwise, so this is inner product on G, right? So on the induced space, inner product on G.
You're going to intertwining operators here?
No. This is kind of formal, kind of Fubini, plus using invariance of the GL2. And then the second step, so this is the first step. The second step.
What was I? I is the induced representation.
Yeah, so W and W check are the induced representations. W psi and W psi inverse.
This from where?
So induced of pi, but realized on the Whittaker realization.
But you're integrating over this Heisenberg group.
Yeah. Is it believable? Anyway, that's what we get. Okay, and therefore, if you just integrate, so this is just the inner integral, but of course if you do the outer integration, at least formally, so the same expression as above, you will just get the same thing with the n. Remember, so the v was just the outer layer, and then you have this other simple root, the long root, so you get the same thing. Of course, this inner product is for two Schwartz functions, just the usual one. Okay, and then you have the psi n. I'm not sure it's consistent. So this just means this is character. So on this x minus x, y, this is just psi of y, just in the middle. Psi n. So this is just a formal consequence. Vn. So the full n is the full maximal unipotent. And now, so if I now specialize to, yeah, okay, no, I still, okay, and this is equal to, again, by some manipulation, now I have integral over the throw. So I just basically do Buhat. Of the SL SP2.
How does it act on the oscillator representation?
Well, I have the full G prime V acting. That certainly contains n. Well, of course, I split the n part in the metaplectic cover. I mean, I have
it's contained in this product. Yes, okay.
Okay, and now this is by just using Bourgeois decomposition, I can write it. So I want to kind of split the variables, right? I want to get a product. I cannot do it at this level, but what I can do is write it like this. So okay, there is some convolution here. Let's not worry about this. So it will be some integral of some product of functionals. I'm sorry it becomes a little technical, but it's the nature of things. So something like that will be, what is this thing? So there will be some power of t. Let's ignore this, and then it will be this integral. Okay, x, y, z. Okay, some element which doesn't matter, psi x dx. So I have some explicit, so this has some invariance property, namely with respect to this group after conjugation, and I have an expression which is kind of symmetric in the W and W check, but there is a T which still somehow I have to separate it. So the only way I can separate, of course, is now to say, so far this is for NES, and now the claim is that we show that actually when I take now, finally, when I take the m half W, So this is some convolution. You can ignore what this means. So the claim is that this will be equal to this M for all t. So at the special point, this will just become a constant. That's why it splits, because it's just a constant. And then the other guy, I can just integrate. And that's for any w. This will also be basically the same thing. Okay, there is some appropriate.
I'm sorry, I'm not following. What are these all?
Okay, so let's just do it again. So first I'm saying that kind of on a formal level, I can compute what's there as some kind of inner product now on F star. But what I have inside is some explicit functionals invariant, which have some invariance. Now, of course, hidden here that there is a uniqueness for this invariant functional just for the Lagrange quotient. So that would make it so this thing will be the same a priori up to a constant, but depending on t a priori. But the miracle is that it's actually independent of t, and so that's where I use the smallness of the m half pi. I mean, it has several kind of.
What kind of functionals are these in the graph?
So these are invariant functional under. So these are.
Can you write down what functionals they are, and what space, and what kind of properties they have?
Okay. So these b's. So b is an invariant functional, or equivariant functional, rather, for the group. What I wrote there, right? This x, y, z. This u, right? That's the u. Goes to psi x. So it's some specific character on this unipotent radical, and I claim that t is a variable, and this the claim, of course, is that home of this for this Lagrange quotient.
But this is defined only for
Of this u, sorry, of this psi u. Let's call it psi u. That this is one-dimensional. Of course, for the full induce, that's infinite dimensional. But for the Lagrange quotient, it will be one-dimensional. I mean, that's, of course, the fact that you have to prove. But, I mean, it's not kind of absolutely necessary, but you cannot hope to prove such a thing without knowing that.
So it's one-dimensional, and hence it is the Whittaker function.
And hence it's proportional to this just at m1 half.
It is Whittaker function.
Right, right. So, I mean, you can, the point that you can go between, so, of course, this space is isomorphic to the Whittaker, you know, to the Whittaker home, so home of this descent, kind of, okay, abstract descent, so to speak, to the psi n. So the abstract descent is this co-invariance under with the Weyer representation. What this expression incarnates.
This u is a smaller subgroup, right? So it's
Right. So.
But by at least the one, the spaces are the same.
So I think one of these equalities. I mean, there are several, but I think maybe this equality is actually kind of a formal thing, which is true always. I mean, okay. I mean, the descent was when I plugged m half pi, but if I did put the m half pi, I did the formal equivalence property of the descent, I would get this equality.
But at least the one, because otherwise.
No. So I'm saying that there is some equality of two things, which is actually formal, always
U
true.
seems much smaller than the n.
Yeah, but I have also the Weyer representation, so I think it is true for every representation. So in other words, when I take the, so let me just write down statement. So the claim is that this statement, if I put anything, is the same or isomorphic to home. Now I have to be careful how I say it. So maybe something like pi tensor omega pi. I mean this very representation, omega psi, and I will have this psi n prime. Okay, I mean, you have to take it with a grain of salt, but you can make some true statement out of this.
Can I add something? The initial formula that you're trying to prove,
Yeah.
it is equivalent to the Plancherel formula for the Whittaker model of design.
Right, that's actually the last comment that I wanted to take. So this is all equivalent to, so it's equivalent to the formal degree relation. Which reads that this d pi prime, let's just write it, make sure I'm not making a mistake. Page 7. Yeah. Okay, so it's basically half of gamma 0 pi symmetric square, which comes as a quotient of these two L factors. Right? The numerator and the quotient of this and this is the symmetric square. But now I'm doing it locally, of course. There is also some factor that you can safely ignore, which is only a 2. So I think it's yeah. So in fact, this is, as you said, this is equivalent to this formula. And actually, that's useful also because in the Archimedean case, well, we don't. I mean, it's a bit painful to deal with these integrals, and we don't do it in the Archimedean case. But in the Archimedean case, I mean, this equivalence is kind of formal. There's no problem to do it in the Archimedean case, and then you can use the fact that you know what is the formal degree in the Archimedean case, so thanks to Harishchandra.
Maybe I missed something. So Ginsburg, Wallace, and Sudri developed this without analyzing these other factors. Is that what the story is? And you've now reduced the full Waltzberg formula to this level individual.
Okay, so they certainly worked a great deal in the local theory itself, but they don't do it kind of in a quantitative way. They tell you, no, this space is not zero, and yeah, no, this is exactly right. I mean, of course, we use a lot their techniques, the machinery, but sometimes you have to, you know, like in football, you have to score the last goal, so you have to stand in the right place when the ball comes. So you just basically make it quantitative, but certainly the ideas are there. They deserve all the credit.
And if that formal degree equivalence is straightforward, and that's not now written.
Yeah, so that came kind of as a surprise. I mean, this, by the way, this is also, so most of what I described is joint work with Mao, and this is also with Chino. Of course, we do it in high rank, but I don't have time to explain this. Yeah, it's nothing. I mean, it just came as a surprise. It's kind of a bonus.
So in higher rank means.
So the high rank picture is going between GL2n and SPn tilde, and okay, indirectly with the SO2n plus 1. So here you have theta correspondence, which is well understood, certainly in the generic case, now even more than that. And this is where the descent comes from. So it gives you a nice picture how to go between both globally and locally.
Again, Ginsburg rather would
Yeah, so this is the GLS descent. Now in the other, so this is actually in this direction. Now in this direction there is of course the lifting, so the Cogdell, Kim, Petesky, Shapiro, Shady lift using converse theorem. And this, these two errors, they are, in fact, so they are inverse to each other. I mean, of course, for the right space of function, I don't have time to describe it exactly. But I mean, even this fact is not, it's not entirely clear. I mean, almost everywhere you do the analytical computation, but you still have to supplement it with local facts. Yeah. And so Zhang and Sudri goes into great detail to explain what happens locally for this case. Unfortunately, the other are not as well documented. I mean, what happens? I mean, you can do it for other classical groups like SO2n, oh no, O2n, strictly speaking, and SPn instead of this. And unitary group. So the unitary group picture is basically the same, but this picture is a little different. It's not Fourier Jacobi, it's really just Fourier coefficients. But unfortunately, it's not as documented, as well documented as in the other case. So even to make sure that these errors are inverses to each other, I think it's not, maybe there's still some fine issue.
Identity in this generality, you compute all these local things, you reduce it to a local thing.
So this local identity, which I wrote down, where is it? Yeah, I should have circled it. Yeah.
That's general.
So that's general. Almost even to the letter, it's the same. I mean, okay, the exact functional, maybe it's more complicated. I need to, but there is an analog generalization of what this functional is and how these integrals look like. So what I explained here is pretty general, but of course some details are different.
But in the formal degree part?
Yeah, the formal degree part is formal. I mean, how to go back and forth between this local identity and the formal degree is very simple, and that's explained in this paper with Ichino. And it's, yeah, I mean, it's just one line. This part is simple. It really came as a surprise, but maybe it shouldn't have. I mean, some people understand it better. Okay, so I think it's.
Maybe you can rewrite your formula in general.
Okay, so let me just make the statement, and I mean the formula is the same, but let me just make the final statement, and then we can stop here. So. Yeah. So I write the global formula and the local formula without, I mean, so there would be some black boxes here, but just in terms of formulation, it's not a bad idea. So, yeah. So the theorem, so this is with Mao. So let pi tilde be the descent, which I won't explain, of pi 1 up to pi k. So this is an isobaric direct sum. So pi I is Caspar representation of GL 2ni, such that L half pi is not 0. And they are distinct, by the way, non-isomorphic, or actually physically distinct. There is multiplicity 1 here. So this is a black box. So then, for any phi in the space of pi tilde, this is a representation of SPn tilde, generic representation of SPn tilde, and I want to compute the Whittaker coefficient square. So the answer is that this will be, okay, so maybe the most interesting factor is 1 over 2 to the k, so that somehow knows about the k here, and then I have some factors which just account for some measure. And then I have so this is pi. So it's an automorphic representation of GL2n. So n is n1 up to nk. So automorphic representation of GL2n. So it's an Eisenstein series of these guys over L. So this is just the product of these ones. And then I have the 1 pi symmetric square, which is non-zero because each one of these is non-zero, and then they are distinct. And then this volume of n of prime. Yes. These are the n integers. It's a lattice here, and inverse, and then n prime of fs. The stable integral. And so that's under the assumption that pi infinity is discrete series. And of course, f is totally real. Again, because of the analysis.
That's a strange assumption for you.
Yeah, it's just a laziness assumption. I mean, it shouldn't be really there. But and also to make sense of this, you have to be careful. So in this case, at least this makes sense without any problem.
You mean just to handle Archimedean integral?
Yeah. I mean, this local identity. I mean, because to justify it, I mean, you have to struggle with all these integrals you do not converge. So there is some ad hoc way to make them meaningful. But in the Archimedean case, it's pain. So this is a caveat, but fortunately, we can use the formal degree to, at least in this case, to ignore this thing, because the end result somehow is equivalent. Okay, so this is true, and then the local, so that's with Ticino and Mao. So if pi tilde is a generic discrete series, which lifts to the same thing, so induced from pi 1 up to pi k, where pi k, pi I are distinct generic it's co-integrable. I mean, okay, it's GLN, huh? Co-integrable. And so locally the condition is that pi I external square has a pole. There's no L-half condition here. Then the formal degree formula, which is very similar to here, holds, namely you have this same factor 1 over 2 to the k, and okay, you have this strange factor just at the prime 2, and then gamma 0 pi symmetric square. So this is pi. And of course, this is for suitable measure, depending on psi, but not on pi, of course. And okay, this is the Peterson inner product with volume 1. So I think everything is on the board as far as statements are concerned. And of course, so as a prerequisite for it is that the descent forms a bijection between the set of representations. So you could cover everything here. And of course, the formal degree, this will only cover for generic, but an argument of Shahidi using what later Arthur did gives that formal degree. Okay, so that also gives formal degree for SO2n plus 1, same formula, except this factor. This is because of work of Gunn and Ticino, that you can transfer. I mean, in principle, you could run the same machine for the SO2n plus 1, but there's a shortcut because Wittek and Atsushi, they show that the formal degree is actually invariant under theta correspondence, so that you get for free. And then you can get formal degree for any representation of SO2n plus 1, simply because, I mean, this argument shows that the formal degree is constant on L packets. I mean, Shahidi proved it conditionally on character identities, but once you have them, thanks to Arthur, then, I mean, the argument is actually not so complicated, because the formal degree is the coefficient of the 0th term in the germ expansion of the character. So if you have character identities, it means that this coefficient is constant. But okay, that's kind of, I mean, we only say things about the generic thing, and then using, and this kind of. We don't say anything interesting about this part.
The genericity of the template package was known before afterwards?
No, of course you need to know plus, okay, plus the fact. So that's also thanks to Arthur that and every generic has every square integrable is has a generic member in the L packet, or every square integrable L packet has a generic member. Yes, of course that's also part of Arthur. So this we just use as a black box, so we don't say anything original here. Yeah, I think it's enough for today. Thank you.